To build the real number system, mathematicians started with a simple concept, a sequence. Think of a sequence as a machine that produces numbers one by one. You put in a step number, and it spits out a mathematical result. The exact order is strictly controlled. This diagram maps how the machine works. At step 1, the notation a sub 1 corresponds to an output of 1.4. Step 2, a sub 2, gives 1.41. Step 3, a sub 3, yields 1.414, and the process continues infinitely. Some machines produce numbers that eventually settle down, a property known as a regular sequence. Imagine two friends walking toward the same house from different directions. At first, they are far apart, but as they approach their destination, the distance between them shrinks. We measure this settling process using a tiny variable called epsilon. If you demand a billionth of an inch of accuracy, the gap will eventually fall below that threshold and stay there. Passing this epsilon test proves the sequence is permanently stabilizing. It guarantees the numbers are locking into a specific target, even if we haven't yet calculated exactly what that final target is. An infinite sequence never actually stops at its final destination. But in higher mathematics, we define the real number as the destination itself. The sequence is simply our set of directions for getting there. This model tracks a sequence of ordinary fractions, 1, 1.4, 1.41, and 1.414. They are advancing steadily toward a specific coordinate. That fixed destination is the square root of 2, an irrational number that cannot be written as a simple fraction itself. Rather than assuming irrational numbers exist in the gaps between fractions, we can use precise, stable paths of rational numbers to mathematically construct them. Defining numbers as infinitely long sequences changes how we perform calculations. We have to establish how to add or multiply these infinite lists together without breaking the system. Addition occurs by aligning two sequences, adding corresponding steps term by term to create a new row. Subtraction and multiplication follow this same rule, keeping the final output stable. Division also works term by term, provided the denominator sequence does not settle on 0, preventing an infinite spiral. By strictly aligning matching steps, these abstract mathematics behave identically to the numbers used in standard arithmetic. Two sequences can begin with entirely different values, yet settle into the exact same mathematical destination. We define two sequences as equal if the gap between their paths eventually shrinks to 0. If the distance becomes smaller than any chosen epsilon, they represent the same location. Inequality requires a permanent, uncrossable positive gap between their destinations. This system incorporates ordinary whole numbers by treating them as constant sequences. A number like 5 is simply a sequence that repeats the value 5 at every step. If we subtract the sequence for 0.9999 from the constant sequence of 1, the gap is 0.1, then 0.01, then 0.001. The difference constantly decreases, falling below every possible positive epsilon threshold we can set. Mathematical equality is defined by the physical impossibility of squeezing any additional value between two sequences. Because no gap can exist between 0.9999 and 1, they are the same number. By treating regular sequences as numbers, we can bridge the spaces between fractions. This process populates every microscopic coordinate on the number line, resulting in the complete set of real numbers. Georg Cantor and his contemporaries pioneered this rigorous logic in the 19th century. They sought to define numbers through precise rules, rather than relying on geometric intuition alone. Calculus relies on limits, which are processes where values get closer and closer to a target. For these limits to be valid, the number system must contain every possible target value, leaving no gaps for a calculation to fall through. If the number line were a sequence of isolated points with holes in between, the math of motion and change would break. The sequence construction ensures a solid, hole-free continuum. The real number system is a product of meticulous engineering, where every coordinate is built upon an infinite stabilizing sequence.